Hi everyone, I'm Anunay, and today I will talk about foreign intelligence surveillance. Specifically, I will describe an open policy problem that's been open for many, many years, and how finally we may have a solution grounded in cryptography. So let's dive in. So in 2008, the US government realized that American companies store data on many foreign customers inside the US. However, the government requires a warrant usually to access these data. So a compromise was sought, and Section 702 of the Foreign Intelligence Surveillance Act was passed. Section 702 allows the US intelligence community, or the IC, to collect communications inside the US when targeting foreigners abroad. The structure of Section 702 has prompted significant controversy, especially due to incidental collection. While the targets of Section 702 surveillance have to be located outside the US, they often communicate with people located inside. The IC ends up collecting these communications incidentally. Let me explain that with an example. So suppose an element of the intelligence community, the NSA, serves a Section 702 directive to email service 1, targeting Mallory at email1.com. Mallory is located outside the US, and the intelligence community knows this. But Mallory is communicating with Alice, who is located inside the US. Alice uses alice at email2.com. Now, the IC element knows that Mallory is not in the US and that they have incidentally collected on Alice, but they don't know where Alice is. Only email service 2 knows anything about Alice's location. The table illustrates what party knows what. So members of both houses of Congress and civil society groups have repeatedly asked the IC for an estimate. Almost every year, letters to that effect are sent to the Office of the Director of National Intelligence. The intelligence community maintains that they cannot estimate incidental collection without a massive manual effort and without infringing on people's privacy. In this paper, we propose a possible way forward. So incidental collection can involve either persons located inside the US or US citizens outside the US. We focus on the former and only estimate the scale of incidental collection affecting people inside the US. As in the previous example, service providers may know the location of their users. Many service providers collect country-level location information for business reasons. So they can build a set of identifiers, like email addresses or phone numbers, that they believe are used by persons located inside the US. The IC element, similarly, can build a set of identifiers they incidentally collected on. So suppose the IC element holds X0, the set of identifiers whose communications were incidentally collected. Each service provider holds a set XI, the set of identifiers associated with users they believe are in the US. The IC element also holds V, which is a set of associated values, suppose the number of communications collected per identifier. Our aim is to privately compute the sum of values in V associated with identifiers in I, where I is the intersection of the IC element set with the union of all sets held by service providers. I is exactly the set of identifiers controlled by persons believed to be in the US who were incidentally collected on. These sets are huge. The service providers may have billions of elements in their sets, and the IC element at least will have millions. So here are the ideal functionalities. We term this problem multiparty private set intersection with union and sum, or MPSIU-Sum. In the paper, we first extend the Apple private set intersection protocol, the Apple PSI protocol, to the multi-party case. And then we build an MPSI protocol out of it, and then extend that resultant MPSI protocol into MPSIU-Sum. In both protocols, a delegated party receives the result. In this case, that would be the IC element, which could then include the estimate in its annual transparency reports. I now describe the threat model. So no participant of this protocol learns any new information about the location of a user associated with an identifier. Similarly, no service provider learns any information about identifiers whose communications were incidentally collected. Our constructions are secure against such information extraction, even against a malicious IC element or a coalition of malicious service providers. As is the case with MPC generally, we cannot prevent participants from intentionally inducing errors, as they can cheat with their input. We also cannot prevent participants from revealing known information through out-of-band channels. And the output of the protocol itself may leak information about the service provider's input sets to the IC element. So in the paper, we discuss ways to mitigate this risk. Our method still suffers from significant limitations. We only generate an estimate of the scale of incidental collection, not a definitive count. We also assume that such an estimate would not reveal intelligent sources or methods. As mentioned previously, these estimates do not include US persons located outside the US. And we can only count identifiers like email addresses and phone numbers, but not people. The protocol also introduces a quantifiable risk of false negatives, so these estimates are always going to be lower bounds. And with these caveats, we will now discuss the design of the protocols. So we require hash maps, which place a value at an index derived from a cryptographic hash of the value. We also require hash to elliptic curve functionality. So for that, we use the current draft of the IETF standard, which can be modeled as a random oracle. As in the Apple PSI system, we require the Diffie-Hellman random self-reduction. So if L, T, and P are 3 elliptic curve points, we call them a decisional Diffie-Hellman or DDH tuple if there is an alpha such that L is alpha times G, the generator of the group, and P is alpha times T. And then we define an operation called DH reduction, which transforms these DDH tuples into DDH tuples and non-DDH tuples into independent random values. Also, we note that the DDH tuples in general have a nice additive property that we exploit in the paper. Our construction also requires a distributed version of the Elgamal cryptosystem. So data encrypted under an aggregate public key can only be decrypted jointly by all parties. As we encrypt values in the exponent, decryption amounts to computing discrete logs. Fortunately, we only need to decrypt one ciphertext, and we use a combination of CRT and the baby step, giant step algorithm to achieve that. So the key insight here is that without knowledge of alpha, DDH tuples cannot be distinguished efficiently if the DDH problem is hard in the group. The delegate, the IC element P0, constructs a hash map that reveals no information about its input set. And then using that hash map, service providers jointly construct another hash map such that slots of this new hash map R correspond to the intersection. Corresponding to the intersection yield DDH values. And without knowledge of alpha, other service providers cannot distinguish which slots correspond to the intersection. And using R, the last service provider, Pn-1, constructs an encrypted array, B, such that the IC element can only decrypt elements corresponding to DDH tuples, or in general, corresponding to the intersection. And finally, the IC element receives this array and can compute the protocol result. So in delegate start, the IC element generates alpha, publishes L, which is alpha times G. This is in some sense a commitment to alpha. And then for each identifier in its set, the IC element maps it onto the elliptic curve and multiplies the elliptic curve point by alpha. The associated value is also encrypted. And then these two values are stored in the hash map at an index associated with the identifier that all service providers can also compute. And then unfilled slots in this hash map are just filled with random data. The last service provider encrypts every slot of this hash map using a different key, and then aggregates all ciphertexts into an array and shuffles the array. The IC element can only decrypt elements associated with the intersection, and the shuffling ensures that they cannot map elements back onto the previous hash map. And then for each index in the array, the IC element attempts to decrypt it. The number of successful decryptions is the size of the intersection, and the decrypted values are Elgamal ciphertexts encrypted under an aggregated key. Then all these Elgamal ciphertexts are aggregated, summed, or whatever operation you want to do. And then after this step, all parties run a joint decryption protocol, and the IC element learns the plaintext sum. Here's the full MPSIU-Sum protocol, and variants for MPSI, MPSIU, and MPSI-Sum are described in the paper. The key insight here is that every party sets slots in hashmap R to definitively be DDH tuples. These slots correspond to identifiers that they have in their set. Other slots, which correspond to identifiers not in their set, are randomized by applying the Diffie-Hellman random self-reduction. So DDH tuples remain DDH tuples, and then non-DDH tuples remain non-DDH tuples. Computation in general is linear to the size of the hash map and also linear in the number of CRT moduli used. We implement and benchmark our construction. Even on large sets containing millions of elements, the protocols conclude within a few minutes. And our implementation is open source and available on GitHub. And as you can see, the false negative rates are also pretty minimal. In fact, they're quantifiable. And if you use a larger hash map, you can lower the error rates. MPSI protocols have been constructed from a variety of primitives. Of these, only Kolesnikov provide benchmarks for large input sets, but their protocols are not secure against collusion. When sets are unbalanced, in that the delegate has a much smaller set, our protocols are faster than past work, but increase communication. MPSIU-Sum has not been studied extensively in the multi-party case for large input sets. To the best of our knowledge, intersection with union in general has not been formalized before for the multi-party case. And we describe many extensions in the paper. I will note a few here. We can prevent collusion between the IC element and service providers using a simple extension. As mentioned previously, adding noise to the estimate might be valuable. And these protocols can be generalized using fully homomorphic encryption to compute arbitrary functions of the intersection, not just the sum. And finally, the protocol result can be computed by an external party with no input, which is useful for transparency reporting purposes. But thank you so much, and please send questions to my email address. And I'll take some questions now.